Hello everyone, today we'll discuss chapter 4, namely properties of working fluids. In Thermo 1, we give you an introduction of the internal combustion engine and we assume that the working fluid composition stay the same, namely pure air. In this chapter, I will show you that the composition of the working fluids change during the engine operating cycles. This is the content of this chapter. First, we will have a look on the working fluid composition and then gas properties, exhaust gas measurement, and the last topic is about equivalent ratio determination from exhaust gas constituents. Let's take a look on the working fluid composition. This table is showing the composition of the working fluid for the spark ignition engine in the second column and the compression ignition engine or diesel engine in the third column. On the first column, it's showing a different engine operating stroke. So the first stroke is the intake stroke. And you can see in here for the spark ignition engine during the intake stroke, we have a working fluid consisting of air, and then it might be a fuel, okay, if we have PFI, okay, port fuel injection, or it might only contain air, and then might be plus recycled exhaust. So in the new engine technology, it has an exhaust gas that is recycled back to the engine for having a better NOx emission. So we will have a look this one in more detail in chapter 11. And it has also residual gas. So this residual gas is the burn gas from the previous cycle. So although we have an exhaust stroke, not all burn gas will be expelled from the cylinder chamber. So some of this exhaust gas stay inside the chamber and will go to the next cycle. Okay, so if we have a GDI, okay, if we have GDI, then in the intake stroke we don't have a fuel. Okay, so in the intake stroke we might have air plus recycled exhaust, if any, or it's only contain air and residual gas. On the next column, what is the composition inside the diesel engine during the intake stroke? So we have air, and then we might have a recycled exhaust, once again to improve the emission, and we have residual gas. And you can see in here, we don't have fuel during the intake stroke inside the diesel engine. Why? Because the fuel is injected at the end of the compression stroke. Okay, go to the next one. During the compression stroke, in the spark ignition engine we have air and we have a fuel vapor. Okay, so once again, depending on when is the fuel is introduced into the engine, we might still have some liquid, okay, if it is GDI, or we might already have close to 100% fuel vapor if it is PFI. And then same thing, we might have recycled exhaust and residual gas. And then in the diesel engine, we have air, we might have recycled exhaust, and we have residual gas. Okay, and then for the diesel engine, the fuel is introduced at the end of the compression stroke here. Okay, go to next, during expansion, so where we have the combustion. Okay, so especially at the beginning of the expansion process, we still have a combustion process take place. Then for the spark ignition engine, we will have the combustion product here. So we have N2, water vapor, CO2, CO, you can see there. We might still have hydrogen, okay? And then we have oxygen here. Especially if we have lean combustion, we have a decent oxygen amount. And we might have NO and then OH, okay? And then single O, H, and so on. Once again, this is during the combustion process, okay? And then in the diesel engine, we have a similar composition here, which is the combustion product. So N2, H2O, CO2, CO, and so on. And then the last one here during the exhaust, where, you know, some of the combustion product recombine into different species. For example, like CO will be converted into CO2. So during the exhaust stroke, we might still have a CO slightly, okay? Or we might have decent CO if we have a rich combustion. But the main product will be nitrogen, CO2, water vapor, okay? And then if we have a lean combustion, we might have a decent oxygen. And then how about the composition inside the diesel engine during the exhaust stroke? So because the diesel combustion occurs mainly under lean mixture condition, so we have oxygen here. We might have CO, but it is a very low, especially compared to the one inside the gasoline engine. And then we still have nitrogen, CO2, and water vapor. So once again, what we learn here is that depending on which stroke we have, the gas composition inside the internal combustion engine changes with the time. And then how can we estimate the thermodynamic properties of the mixture inside the internal combustion engine? So there are several models to estimate these properties. This table is showing 5 different category of the thermodynamic properties modeling. The first model here is a very simple one. So in this case, the working fluid is assumed as an ideal gas mixture with a constant Cv and Cp. So it's pretty much similar to the cold air analysis we learned in Thermo 1. So once again, this is a simple one. It's useful for illustrative purposes, especially since the specific heat of unburned and burned mixture are significantly different. So, but in here, we assume that the burned and unburned mixture have the same Cp and Cv. Okay, and then the second model here is that we differentiate between the burned and unburned mixture. So, but we still assume it is an ideal gas with constant Cv, but the unburned mixture has its own Cv and Cp, and the burned gas has its own Cp and Cv. So it is more accurate than the first model, once again, because we consider individual temperature of the mixture here, which result in different Cp and Cv. Okay, and then the third model here on the unburned mixture, we assume that the unburned mixture is a kind of frozen mixture. It's called frozen because the composition doesn't change during the process. Okay, so it is a frozen mixture, and then ideal gas at certain Cv, and the Cv is a function of temperature. So in this case, Cv is not constant anymore. Okay, and then in the burn gas, similarly, we assume it is a frozen mixture of ideal gas, and Cv also change with the time. Okay, and then the fourth category here, it assume same thing for the unburned mixture. It assume a frozen mixture of ideal gas, and Cv change with the time. And then in the burn gas, we approximate the thermodynamic properties here as the mixture under equilibrium condition. Okay, under equilibrium condition. And then once we get the equilibrium composition, we can get the thermodynamic properties. And then the last category here is same thing for the unburned mixture. So this is a frozen mixture of ideal gas, and Cv change with the time. But in the burn gas here, we model this burn gas as the mixture of reacting ideal gas in the thermodynamic equilibrium. Okay, so number 4, number 5 here for the burn gas, we still assume equilibrium condition. And actually there is one more category here, number 6. So here it stays the same for the unburned mixture. So this is a frozen mixture of ideal gas, Cv change with the time. But in this one, we assume that this is a reaction rate control. So it means it is not under equilibrium condition. So this is what's going on right now when my team is modeling the combustion process inside the cylinder. Next one is looking at unburned mixture composition. Unburned mixture consists of fresh air and then residual. So this is the burned gas from the previous cycle. It might contain recycled exhaust gas for better NOx emission, and it contains the fuel. So if I make a schematic here, so for example, this is the chamber and this is the piston, and then we might have a flame here. Okay, so the flame propagate to a different direction here. So it means here we have a burned gas, and this one is the unburned gas or unburned mixture. So this unburned mixture consists of this one. Okay, and then there are several parameters to get an estimation of the composition inside this unburned mixture. For example, if you want to know how much is the residual fraction, okay, so in here we have a residual fraction XR. So this is the ratio of the residual mass, so MR, over MC. So MC here is the trapped mass inside the cylinder, okay. Once again, MC is the trapped mass inside the cylinder. And then the next parameter here is the EGR percentage. So this is the ratio of the EGR mass over the induction mass. So this is the mass flow from the intake system into the cylinder. Okay, so this one is mainly air, and then might be a fuel and EGR itself. But MI here is the induction mass going into the cylinder from the intake port, which consists of air and EGR. So it's mean we don't include fuel here. Okay, once again, MI here equal to air, okay, plus MEGR. Okay, so it doesn't include the fuel mass. The next one here is the total burn gas fraction. So here we have burn gas coming from the EGR plus the residual. So, and this one is the trapped mass inside the cylinder. Okay, so this three equation is used to estimate the residual fraction or EGR percentage or burn gas fraction. The next one is how can we get the composition of the burn gas fraction in the unburned mixture. So in this case, we use this equation. So this is the single reaction for the fuel. So the fuel is represented by this term, okay, and then react with air, and then the product here is CO2, H2O, CO, oxygen. Here we have hydrogen and nitrogen. So with this equation, we want to know what is the mole number of the burn gas species here, which is CO2, H2O, and so on. So from this equation 4.4, we introduce several parameters here. The first one here is this one. So this is the molar NO ratio. So it is which is 3.773. And then epsilon here equals to 4 over 4 plus y, and y is the HC ratio of the fuel, and this one is phi, the equivalent ratio, and then I here is the moles of species, I here per mole oxygen in the reactant. So you can see in here the number of oxygen mole is 1. Okay, and then our goal here is to get the Ni. So in this case, we calculate Ni by following this assumption. So for lean and stoichiometric mixture, so it means that phi less than 1, we neglect the existence of CO and hydrogen. And then for rich mixture and stoichiometric as well, we neglect oxygen. And then for rich mixture, either we use this reaction, so it's called water-gas reaction. So this reaction of CO and hydrogen result in CO and water vapor. And then in this case, if we assume this water gas reaction under equilibrium condition, then we can get the equilibrium constant. So K here is a function of temperature. I think you learned this one in chemistry class. And then to get equilibrium constant, here we use a curve fit from Janov. And once again, K here is a function of temperature, so equation 4.5. Okay, when we solve that equation for Ni, then we will get Ni for burned gas species, so in this table. So you can see here that the composition is differentiated according to the number of phi. So on the second column here is the composition when phi is less than 1. So it's mean we have a Lynch mixture. And then this one is when we have a rich mixture. So phi is more than 1. So for example, the amount of CO2 here for the Lynch mixture is epsilon times phi. So epsilon, once again, it is, I think it is 4 over 4 plus y. And then CO2 for rich mixture, it is epsilon times phi minus c. And c, do we have equation for c here? So this is from equation 4.6. We don't have it here. Let me take a look in the book. What is c? Okay, one moment. Okay, c here is obtained from this correlation. So it is k minus 1. K is the equilibrium constant. We can use 3.5 here. And then time c squared here minus c. And then here we have k times 2, and then phi minus 1, and then plus epsilon phi, okay, and then it is in the bracket here, and then plus 2, and then 1 minus epsilon phi, okay, and this is this one, okay, and then plus 2k epsilon, and then phi minus 1 equal to 0. So we have k equals to 3.5, and then phi is given whether this is 0.9 or 1.1. Then from this equation you should be able to get what is c, and then epsilon once again is calculated using this formula, and y here is the HC ratio, okay, HC ratio, this is y. Okay, and next one here for CO, if it is lean, we don't have CO, so it's equal to 0. Hydrogen as well, it's equal to 0. And then you have oxygen for leans, it is 1 minus phi. But for a rich mixture, we don't have oxygen. Okay. How about the unburned mixture composition? So the same procedure can be applied here to get the unburned mixture composition, and the result is shown in this table. So the detailed calculation you can check in the reference book. So once again, here we have two columns here for the formula of oxygen, nitrogen, and CO composition. So on the left side, we have a Lynch mixture, we have rich mixture here. Okay, so if it is Lynch mixture, then CO and hydrogen equals to 0. Okay, and on the right side here is for the rich mixture. Next topic is about a gas properties relationship. So most of this relationship has been introduced in Thermo 1 and Thermo 2. For example, to get Cv, so Cv equal to du over dt under constant volume, okay, and Cp, it is dH over dt under constant pressure, okay, and then this is the formula for the internal energy. So this is the reference of the internal energy. This one is for the enthalpy, and this is the formula for the entropy. So it's assumed that the mixture is an ideal gas mixture. Okay, and if you want to get a refresh of the ideal gas relationship, it is available in Appendix B of the reference book. And then next one here, if we define this parameter as the integral of this one, and this one is the integral of this one, then you can simplify this entropy equation. So equation 4.14a, and you will get this one. Okay. And then for the isentropic process, then you can simplify it to be like equation 4.18. And this one is showing an example of the chart for the properties of the mixture, and this one is the unburned mixture, and it is isooctane C8H18, and this shown the sensible enthalpy and internal energy as a function of temperature, and this one is a function of phi as well. So, okay, for example, if we have unburned mixture at 800 Kelvin and the phi is 0.4, then you will get the value of enthalpy and internal energy is around this number. Okay, so this one is good for an illustrative purposes, but when we write a program to get the properties, then we need to use a different method, not by chart, but by using a formula. And same thing here, it is for internal energy versus entropy for equilibrium burn gas. Okay, previous one is for the unburned, this one is for burn gas, and this is coming from the combustion of isooctane, so still C8, with equivalent ratio of 0.4. Okay, so from this chart you can get once again the internal energy and entropy as a function of temperature here and pressure. Okay. Next one is the properties estimation for modeling. For example, in the future, if you want to write a program for modeling a combustion process inside the internal combustion engine, then you need to get a Cp and then H, S, and so on as a function of temperature and might be a function of phi as well. In this case, you need to use a polynomial formula here to get the properties of the mixture. This is showing an example of the formula, polynomial formula, to get a Cp and then internal, specific enthalpy and entropy here as a function of temperature. Okay, and A here from A1 through A7 here, this is a constant, and this constant is species dependent. So for example, if you have a CO, then you will have different A1 through A7 from the one for hydrogen. Okay. Next one is transport properties. So this is an important properties as well. As you might know that inside the internal combustion engine, we have a transport of mass, momentum, and energy. We might have also turbulent transport as well. So the processes by which a mass, momentum, and energy are transferred from one point in a system to another one are called rate processes. So in this case, we need several transport properties to model the transport of mass, momentum, and energy. And in this case, we need to have a viscosity of the mixture and then thermal conductivity, so it's especially for the transfer of heat, or mass diffusivity for the transfer of mass. So, and I'm assuming that you have learned these properties in a fluid of mechanics class. Next topic is exhaust gas measurement. The composition of exhaust gases can readily be measured. So the purpose of this exhaust gas measurement is to determine engine emission. So like CO, NOx. So NOx here is the sum of NO and NO2, and then unburned hydrocarbon, because you know in chapter 3 that not all fuel is burned during the combustion process, and particulate or soot. So this is a special emission for a diesel combustion. The exhaust gas measurement is also used to determine the relative proportion of fuel and air which enter the engine so that its operating equivalent ratio can be computed. We know that we can get the equivalent ratio from the measurement of the airflow and fuel flow, but in almost all of the engine test cell we have, we use the exhaust gas measurement to calculate the equivalent ratio. So from this equivalent ratio, we can get the amount of the airflow, okay, because we also measure the fuel flow. So once again, most of the time, we don't measure the airflow. Rather, we calculate phi first, the equivalent ratio, from the exhaust gas measurement, and then using the resulted phi and the fuel flow to calculate the airflow. So this is several measurement tools that is used to get the composition, for example, like CO and CO2. We use NDIR. Okay, we might use FID to get unburned hydrocarbon. Okay, and then for oxygen, we might use a paramagnetic analyzer. At Southwest Research, we use this one. So we use a gas chromatography to get the composition of CO, CO2, oxygen, NOx, and so on. So one measurement tool to get all exhaust gas species. How is the composition of the exhaust gas inside spark ignition engine and compression ignition engine? Firstly, let's take a look inside the spark ignition engine. So this figure is showing the schematic of the spark ignition engine exhaust gas composition in mole fraction as a function of equivalent ratio here. Okay. And in this case, the fuel is gasoline and isooctane. Okay, so we have two fuel here. So the HA ratio here range from 2 to 2.25. Okay, and then it is taken from a different place. So the solid line here is from MIT, and then DNL here I think is from different lab. Let me check the book. It is from D'Aleva and Lovell. Okay, and then the next one here is from Steve Fender, Harrington, and Shisu. So I believe this is the researcher name. So what you can see in here that all have a similar trend. Okay, let's take a look first on the CO2. Okay, CO2 is maximum when phi equal to 1. So it's very important. Okay, CO2 is maximum at this point. When we have a Lynch mixture, it means it's going to the left, CO2 decreases. Similarly, when we have a rich mixture combustion, CO2 also decreases. Okay. Next one, looking at oxygen. Okay. So if we have a Lynch mixture combustion, so it means we have more air, then the oxygen content is high. This makes sense, right? And then if we add more fuel while maintaining the airflow stay the same, then we have less oxygen in the exhaust gas, and this is where we have stoichiometric, and then oxygen decreases here, although it's slow. Okay, and the next one is CO. Okay, CO for the Lynch mixture combustion, we have a very small CO. It makes sense. Okay, because you have more air, you have less fuel than the stoichiometric amount or than the theoretical amount. So you have enough oxygen to burn or to oxidize the fuel. Therefore, CO amount is low here. If we have a rich mixture combustion, then we start seeing more CO. Okay, you can see in here, as we increase exhaust equivalent ratio, CO increases as well. Okay, same thing here for hydrogen. If we have more fuel, so it means if you have rich mixture combustion, then we have more hydrogen as well. And this is the exhaust gas composition for compression ignition engine. As you might know, the diesel engine operates under Lynch mixture condition. So the data that we have here is with phi less than 1, okay, less than 1. Although I can tell you that several years ago, we have done research looking at the stoichiometric diesel combustion, but it was still under research, okay. So as you might expect that if we have a leaner mixture, then we have more oxygen in the exhaust gas. And same time, we have less CO2, okay, as we have a leaner mixture. And because diesel engine operate under Lynch mixture condition, so it has a very, very low CO compared to the one in the gasoline engine. Next one is equivalent ratio determination from exhaust gas constituent. As I mentioned to you that the equivalent ratio determination is not from the measurement of the fuel flow and airflow, rather it is estimated from the exhaust gas composition measurement. So exhaust gas composition depend on the relative proportion of fuel and air fed to the engine, fuel composition, and completeness of combustion. So from this effect, we can use exhaust gas composition to determine the operating fuel-air equivalent ratio of engine. Okay, and we use this formula, the reaction, so equation 4.55 for the reaction of the fuel here, and then plus the oxidizer here, this is air, and in the product we have unburned hydrocarbon, and then we have CO, and then CO2, oxygen, and so on. So with this formula, we wanted to calculate what is the mole fraction of the burn gas species, and how can we get phi, okay, how can we get phi from this mixture composition of the exhaust gas. So we have several unknown variable here, which is the mole fraction of the burn gas. So, and then we need to find another equation so that the number of the unknown variable is the same as the number of the reaction. So from the test data, the concentration of the inorganic gases are usually measured dry. So it means here we remove H2O. Okay, we remove H2O. For example, the inorganic gases here is CO, CO2, and so on. They are measured dry. Okay, and then for the unburned hydrocarbon, this one, so usually it is measured wet. Okay, from this reaction 4.55, we have 7 unknown variable listed here. Okay, so it's mean we need to have 6 more equation. Okay, we need to have 6 more equation in addition to this one. So we have this carbon balance, and then we have hydrogen balance, oxygen balance, nitrogen balance, and then that the mole fraction of burn gas species add up to 1. Okay, so we have 5 equation here. And then we get one more equation from the water sieve reaction. So this is the reaction of CO2 and H2, and the product is CO and water vapor. So we got equation 4.61 for the equilibrium constant, and in this case we use 3.5, and you will see that the impact of K here is minor. So if you use 3.8, it will have a minor impact to the result of phi. So for the X with a star here, this is the dry mole fraction of species I, but the one without star, so this is the wet mole fraction. Okay, and then by solving those equation, we should be able to get phi following equation 4.65 here as a function of the oxygen mole number and then the wet mole fraction of water vapor, and then this is the wet mole fraction of water vapor as well, and this one is the dry mole fraction of CO, CO2, oxygen, NO, NO2. Okay, so once again, from this equation 4.65, you will get phi from the measured exhaust gas composition. So assuming that you have X here from the testing. And this is the way we convert dry into wet. Okay, so once again, this is a dry and this is wet. So you can apply it for CO, CO2, and so on. And this is another formula that is used to get NP, and then this one is to get the amount of water mole fraction. Okay, this is the formula to get the wet mole fraction of hydrogen, and this one is to get the wet mole fraction of nitrogen. So using this one skin formula, you can get phi from the measured exhaust gas composition. So this is an important formula that is also used at Southwest Research Institute to get phi from the measured exhaust gas composition. Okay, we have completed chapter 4 discussion. Thank you.